Since this airport is at a high elevation, we will need a faster true airspeed for takeoff, but you should use the same indicated airspeed.
Wait, are you saying that the airspeed indicator doesn't tell me my actual airspeed?
Yes, there is a difference between indicated airspeed and true airspeed, and before we take off, you should adjust the altimeter so that it shows our airport elevation.
So, I need to tell the altimeter how high we are? That seems backwards. I thought that the altimeter was there to tell us how high we are. And why did we have to tell the directional gyro our heading? Isn't that its job?
I guess this would be a good time to discuss how these instruments work.
Controlling an airplane requires you to take in information about what the airplane's currently doing and what the air around it is doing. You have instruments to provide that information, but with caveats. You need to be able to interpret what your instruments are telling you and understand some of their potential failure modes. The magnetic compass tells you your heading, but it's subject to some errors. The inclinometer tells you whether the airplane is pointed in the same direction that it's currently moving. The air data instruments, often called the pedostatic instruments, provide information about airspeed and altitude. The gyroscopic instruments provide information about the orientation of the airplane with respect to the horizon. Angle of attack instruments are starting to show up in general aviation airplanes. Instruments associated with the engine will be covered in the lesson on engines, and instruments that are related to radio navigation will be covered in the lesson on navigation. The compass determines your horizontal orientation by measuring the Earth's magnetic field. However, magnetic north is not aligned with true north. The difference between these two is called magnetic variation, and that can be found on an aeronautical chart for different locations. A compass is also influenced by the magnetic properties of different components of the aircraft. The difference between the compass reading and the magnetic heading is called magnetic deviation. That's indicated on a compass correction card. A memory aid to remember which one is which is to recall that magnetic variation varies over time, and that some aircraft are deviant and they want to take you to other places. In addition to magnetic variation and deviation, there are some other compass errors that you need to be aware of. When you are on a north or a south heading, the compass reading is impacted by the airplane's roll attitude. So when you are headed north, a bank to the left will show as a turn to the right. Similarly, a bank to the right will show as a turn to the left. When you're heading south, a bank to the left will show as a larger turn to the left, and similar to the right. There's an acronym to remember this: NOES. This stands for North Opposite, South Exaggerated. Another way to think of this is that the compass lags when you're going north and leads when you're going south. Therefore, to turn to a northerly heading, you need to start rolling out of the bank before the compass gets to that heading by more than what you usually would. The magnitude of this error is strongest when you're on a direct north or south heading. When you're on an east or west heading, this error goes away. The magnitude of the error is also impacted by the latitude. The error is stronger at higher latitudes. When you're on an east or a west heading, the compass reading is impacted by acceleration or deceleration. Specifically, when you accelerate, the compass indicates a turn toward the north, even though your heading's constant. When you decelerate, the compass indicates a turn towards the south.
I haven't even been looking at the magnetic compass except to set the directional gyro. Why do I need to learn to make turns using the compass?
The directional gyro is easier to use, but some airplanes don't have one.
The inclinometer indicates whether or not the airplane is pointed in the same direction that it's moving. In other words, whether the airplane is coordinated. In some aircraft, this is a separate instrument. In other aircraft, this is part of the turn coordinator. So if you're not coordinated and the ball moves off to one side, then you should step on the ball. So if the ball moves off towards the right, push on the right rudder pedal. If the ball moves off to the left, push on the left rudder pedal. Airplanes are required by regulation to have an airspeed indicator and an altimeter. Many airplanes also have a vertical speed indicator. These instruments are called the air data instruments, or sometimes the pedostatic instruments. They utilize two different types of pressure sensors. The static port is a small hole, usually on the side of the aircraft. It's positioned to sense ambient pressure. That's the pressure that the air would have if it was not being influenced at all by the aircraft. Of course, it's impossible to not influence the air, but the designers will pick a location on the airplane that approximates that as well as possible. During your pre-flight inspection, it's important to check the static port to make sure that it isn't covered by anything. When people wash an airplane, it's common to cover the static port to prevent getting water inside. The pitot tube is a forward-facing tube, usually located under one wing. It's designed to sense the dynamic pressure plus the ambient pressure. Dynamic pressure is the air pressure that's related to the speed of the air. A pitot cover is often used to prevent insects from nesting in the pitot tube while the airplane's parked on the ground. The one on the left is designed to automatically open as soon as the airplane gets up to speed. The one on the right must be removed during your pre-flight. If they're not removed for any reason, then the airspeed indicator won't work. The altimeter measures the static air pressure and determines the altitude based on a standard pressure lapse rate with altitude. However, pressure is not only a function of altitude. Pressure also varies at a given location as weather systems move in and out. So to correct for this pressure variation that's due to weather systems, you need to enter a local barometric pressure into the instrument in a thing called the Colesman window. You do that by turning a knob on the instrument. If you don't have the local barometric pressure, but you're at an airport and you know the field elevation, then you can just turn the knob until the altimeter reads the correct field elevation. Let's discuss some of the different terminology that's used for different types of altitude. The indicated altitude is simply whatever your altimeter says. The pressure altitude is the altitude that corresponds to the current outside air pressure without regard to any local weather systems that may be passing through. So your altimeter will read close to this if you enter 29.92 as the barometric pressure, since that's the standard barometric pressure in the pressure model of the atmosphere. True altitude is the actual vertical distance above sea level. Your altimeter will read very close to this if you enter the proper local barometric pressure. Absolute altitude is the vertical distance above the ground, so this will vary as the ground elevation changes. And then density altitude corresponds to the current air density, which is different than the air pressure. This is the pressure altitude which is corrected for any non-standard temperature and humidity. This is what you should use for performance calculations. The airspeed indicator measures the dynamic pressure by comparing the pressure at the pitot tube to the pressure from the static port. Dynamic pressure is a function of the airplane's speed through the air and the air density. The dynamic pressure is converted to airspeed assuming a standard sea level air density. Stall speed, as well as some other important speed references, are influenced by air density in the same way that dynamic pressure is. So this indicated airspeed is more useful than true airspeed for maneuvering the airplane. If the airplane has flaps, there will be a white arc on the airspeed indicator. The white arc represents the flap operating range. It extends from the stall speed in the landing configuration with the flaps deployed to the maximum flap extended airspeed. The green arc represents the normal operating range. It extends from the stall speed with the flaps retracted to the maximum structural cruising speed. The yellow arc represents the caution range. It extends from the maximum structural cruising speed up to the never exceed speed. Operating at airspeeds in this range is only safe when you're in smooth air. The never exceed speed is also indicated by a red line. In some aircraft, VNE is a true airspeed. If you're at a high density altitude, then the true airspeed will be higher than the indicated airspeed. If that's the case for your aircraft, then you'll need to consult a conversion table for your altitude to know what indicated airspeed corresponds to the present never exceed speed. We use different terminology for different measures of an airplane's speed. The indicated airspeed is exactly what your airspeed indicator reads. The calibrated airspeed is the indicated airspeed that's corrected for instrument and installation errors. Calibrated airspeed and indicated airspeed are usually very close together because our airspeed indicators are quite accurate. True airspeed is how fast you're actually moving relative to the air. You can calculate your true airspeed from your indicated airspeed by considering the temperature and the pressure. Ground speed is how fast you're moving relative to the ground. That matters when we get to cross-country calculations. Some airspeed indicators have a true airspeed ring. To use this, the pilot needs to use a knob on the airspeed indicator to rotate the ring such that the outside air temperature lines up with the pressure altitude. After doing that, the pilot can read the true airspeed indicator across from the dial on the true airspeed ring. The vertical speed indicator measures a rate of change of pressure from the static port and determines a rate of change of altitude from that. There is a delay of several seconds between the actual change and the indicator displaying the change. So it's actually showing you your vertical speed from several seconds ago. There are some things that can go wrong with the air data system. If you notice that you suddenly became really good at maintaining your target airspeed or really good at maintaining your target altitude, then you should suspect that you might have a malfunction in your air data system. If the pitot line gets completely blocked, then the airspeed will stay constant even as your actual airspeed changes. As you gain altitude, the airspeed indication will increase. If the line connecting the pitot tube to the instrument has a leak in it, then the airspeed will indicate lower than your actual airspeed. If the line from the static port to the instruments gets completely blocked, then the altitude indication will stay constant. The airspeed indication will decrease as you climb to a higher altitude. Some airplanes have an alternate static source that you can select if you notice that happening. If you recognize any of these malfunctions in flight, the best thing to do is to judge your airspeed based on your pitch and your power setting. You should judge your altitude visually. If you have GPS that provides a altitude readout, you can use that as an alternative to your altimeter reading.
The next set of instruments we should discuss is the gyroscopic instruments. These instruments provide information about the aircraft's orientation.
I thought the gyroscopic instruments were for people that fly in the clouds. Why do I need to know about them?
As a VFR pilot, your primary source of information about the aircraft orientation will be from looking out the window. However, the instruments allow you to be more precise. Also, at night or in poor visibility, the horizon might not be a reliable indicator of orientation.
Gyroscopic instruments are based on the principle that a rapidly spinning disk tends to remain in the same orientation. Inside each of these instruments is a rapidly spinning disk. Some modern replacements for gyroscopic instruments use solid-state electronics as opposed to a rapidly spinning disk. On your artificial horizon, the orange parts stay in position relative to the instruments, and the blue and brown parts stay in position relative to the horizon while the aircraft moves around the instrument. I'm referring to these parts by color with respect to the illustrated example here. The corresponding parts on the artificial horizon in your airplane may be different colors than this. The bank angle is indicated by where this orange triangle is relative to the tick marks on the perimeter of this blue ring. The pitch is indicated by the marks on the central portion relative to that orange bar. The pilot can adjust the orange bar vertically by rotating this knob. That's useful for making the 0 point correspond to the target pitch attitude. The directional gyro provides the same information as the magnetic compass, but without the compass errors and without bouncing around in turbulence. Although it doesn't have the same errors as the compass, it has a different type of error called gyroscopic precession. The precession causes it to gradually creep off from the correct indication. We deal with this by using the compass and the directional gyro together. Whenever the compass is in a stable condition, you turn a knob to adjust the reading on the directional gyro so that it agrees with the reading on your compass as corrected by the compass deviation card. Some directional gyros also have a heading bug. You set that using a second knob. This is a useful way to remember what heading you're trying to steer to. In aircraft that have an autopilot, the heading bug may be how you communicate to the autopilot what heading you want it to maintain. The turn indicator tells you your rate of turn. It is not telling you your bank angle, although bank angle and rate of turn are related quantities. Tick marks indicate a standard rate turn. A standard rate turn is 3 degrees per second or 2 minutes to complete a 360-degree turn. When the turn indicator is integrated with the inclinometer, it's referred to as a turn coordinator. Gyroscopic instruments need power to keep the disc rotating. Usually the artificial horizon and the directional gyro are powered by vacuum, and the turn coordinator is electric. But there are exceptions to that. Some aircraft have different systems. It's important for you to know which instruments use which power source in your airplane. If there's a failure of either power source, you need to know which instruments you should stop trusting. In modern aircraft, vacuum is provided by an engine-driven vacuum pump. In older airplanes, vacuum for instruments may be provided by something called a venturi tube. These only work when the aircraft is moving fast enough. So the gyroscopic instruments in these airplanes will not be working until after the takeoff.
So that thing on the side of the airplane isn't a horn?
No, it isn't a horn. It is a venturi which powers some of our gyroscopic instruments.
Then how do we beep at people when we want to tell them to get out of our way?
We don't do that.
There's a standard arrangement for the 3 air data instruments and the 3 gyroscopic instruments. This standard arrangement is often referred to as the 6-pack of instruments. If you have opportunity to fly an airplane that is built in the 1940s or 1950s, then the instruments may not follow this pattern. A lot of newer aircraft have glass cockpits as opposed to the standard 6-pack of instruments. Aircraft with glass cockpits have a screen called a primary flight display, which includes all the same information as the standard 6-pack, but it's displayed in a different format. When you transition from an airplane with a 6-pack to an airplane with a glass cockpit, or vice versa, it takes a while before you'll get comfortable knowing where to look for various types of information. Once familiar with the display, most pilots feel that the primary flight display is easier to interpret and provides more information than the 6-pack of instruments. Since an airplane always stalls at a particular angle of attack, but can stall at different airspeeds, angle of attack is useful information for a pilot. Using a given angle of attack for approach, as opposed to using a particular indicated airspeed, automatically corrects for changes in the aircraft weight. However, until recently, angle of attack instruments were not common in general aviation airplanes. That's changing. A number of manufacturers have started to offer retrofits, and new aircraft are starting to come with angle of attack sensors and angle of attack indicators. At this point, there hasn't been any standard that has emerged about how angle of attack information should be displayed to the pilot. The picture below here illustrates one manufacturer's approach to displaying that information. A primitive type of angle of attack sensor called a stall warning horn is common on general aviation airplanes. There is a point called the separation point along the front of the wing. Air above that point flows over the top of the wing, while air below that point flows under the wing. The separation point moves down as the angle of attack increases. At an angle of attack near the stalling angle of attack, a tab gets pushed up, and that triggers a stall warning horn in the cockpit.
There sure are a lot of instruments in this airplane. What if something breaks? Do we have to just wait until it gets fixed to use the airplane?
That depends on which piece of equipment breaks. Some instruments are not required. If those break, we just need to remove them or mark them so that we don't forget that they are not working. Even for required instruments, I will train you how to get on the ground safely if they break in flight.
So what equipment needs to be working in order for the aircraft to be airworthy? For some aircraft, there is a minimum equipment list. This is a document that is approved as part of certifying the aircraft, and it lists which things need to be working in order for the airplane to be airworthy. If the airplane does not have a minimum equipment list, then there's a set list of instruments that need to be working. The airspeed indicator, the altimeter, the inclinometer, a compass, a tachometer, and an oil pressure indicator. If you're operating in certain classes of airspace, then there may be additional equipment that is mandatory in that airspace. If any instruments are not working, here's the test for whether the airplane is still legal to fly. First, is the instrument required according to either the minimum equipment list or the standard list? If not, the instrument has to be either removed from the airplane or marked as inoperative so that a pilot won't be confused and accidentally follow instruments that are telling him wrong information.
Most of the time, our instruments do a good job of providing the information that we need. I hope you now have a good understanding of what each instrument is telling you. Sometimes, you need to help your instruments out by providing them with some information.